So I am redoing the entire lesson from this morning because I thought my delivery sucked and it was running long, and I wanted to make it a little bit more condensed for you guys. We really got through the increasing and decreasing functions. Ultimately, this fancy this fancy vocabulary definition is just saying that sometimes they're increasing, right? Sometimes you got a graph that's increasing, sometimes it's decreasing, and then sometimes it's constant, right? That's a terrible constant. Constant's a straight line. So keep in mind that we'll see it better visually than we will with the definition. So I'm not going to go into a long extended description of the definition because we've already kind of talked about that. Here, when we're talking about increasing, decreasing, or constant behavior of each function, if we look at these different graphs, we can kind of see what's going on here, right? This one, we're talking about behavior from left to right. So the behavior of this equation from left to right at every point is going up. At every point, it is increasing. And so what we would say about this is that this function is increasing at every interval, right? This is an increasing graph, right? It is always going up from left to right. I want to make these make my markers a little skinnier. Here, when we look at this one, it's going to change at intervals, right? In the beginning, if we're looking at it from -2 all the way up to -1, we would say that it's increasing, right? Increasing. But if we look at it in terms of -1 to 1, what's happening from here to here? Well, from left to right, it's decreasing. And then again, we've got from 1 to, not even -1, it's just 1. From 1 to 2, it's going back up again, right? So we are increasing. So you can usually visually tell what's happening here, right? Here, we're saying if t is less than 0, so in any case, t is our input variable, right? So it would be kind of our x. It's what's running along this axis right here. You can see there's a t. Saying if t is less than 0, right, we are decreasing where t is less than 0. We are increasing because we're reading from left to right. Where t is less than 0, we are moving up. We are increasing. From 0 to 2, we've just got a constant, right? There's no slope at all. And then from t greater than 2, anytime we put in a t value greater than 2, we are decreasing. And so you can actually kind of figure these out just by looking at the graphs. And I don't want you to spend a whole lot of time worrying about it because you can figure these out just from the graphs alone, right? It's just a matter of figuring out which interval we're working on. So let's see if I can get this slide up all the way. So this is what I was just telling you. We just went over the graphs of all of those in the last slide. This is just the actual solution to those, but we actually did them on the slide, so we're going to move over here. So it says here, to help you decide whether a function is increasing, decreasing, or constant on an interval, you can evaluate the function for several values of x, which means that you can input different numbers to determine how it's going to behave. And it says, however, you need calculus to determine for certain all intervals. So we can get an idea using algebra, but we would really need calculus to understand this for every curve. But this is pre-calculus, which is why we're discussing it. The next thing we're talking about is minimums and maximum values of the functions, right? And what we're saying is that anywhere there's an interval change, we have what we call relative max and mins, right? A relative minimum is anytime we have a point on the bottom where we're changing direction. So in this case, I would have a minimum here, and I would have a minimum here, and I would have a minimum here. These would not be mins. The reason is there is no change in direction here, right? But here we're going from decreasing to increasing, from decreasing to increasing, decreasing to increasing, and those would be our relative mins. So in that respect, we can say that the same thing for our relative maximums, right? That when we're going from increasing to decreasing, we're going to have these points here that will be what we call our relative maximums, right? In the same respect that this is a min, this is a min, this is a min, these are our maximums. The basic way I could tell you to know is it is a point of change, right? We have to be changing direction, right? If we're changing direction at the top, it's a maximum. If we're changing directions at the bottom, it's a minimum. And that's the best way I can think of to describe what's going on. So here you can show different examples, right? Even though this one is higher, these are both still maximums because with both of them, we've got a change in direction, right? We've gone to the pinnacle of height there and came back down. Here it's a minimum because we've gone to the bottom height for this specific curve and then changed direction. So it's at our direction changes that these minimums and maximums occur. I don't remember how many of these I have. 4. Okay. So you will study a technique for finding the exact point at which a second degree polynomial function has a relative minimum or a relative maximum. You've done it before in Algebra 2. It deals with quadratics. Remember when we had the parabola, you could always figure out the vertex, right? And by using minus b over 2a. And it would give you the vertex, whether that was a minimum or a maximum. And a 2-degree polynomial, a second degree polynomial, is a quadratic. And you guys know how to solve quadratics. But we aren't getting to that today. Ultimately today, we're just trying to get you to be able to look at a graph and be able to tell me the intervals in where it is increasing, decreasing, or constant. Average rate of change is just slope. It's fancy for slope, but that's what's happening is we're finding a rate of change. And this is where we kind of lost it during class today, so I want to be pretty thorough with this. We've learned that a slope of a line can be interpreted as a rate of change, but now we're talking about a rate of change between functions, which means that we're going to have to figure out what y is sometimes, given an x, right? But technically, what we're saying when we have x of 1, comma, f of x of 1, right, is the same thing as saying x1, y1. It's what is y when we input this x value. And so what we're looking for is we're going to be looking at, for the slope, is f of x of 1 minus f of x2 over, I don't know how I made that. Let's get rid of that sucker. I don't even know what that is. Over x1 minus x2. Now I could write that as x2 minus x1 as long as I had the above the same. Doesn't really matter. They're arbitrary because I get to determine what point is what point, right? So what is that going to look like? Well, it's the same. They just wrote it up there. So we're looking at a change in y, the difference between our y values over the difference between our x values. And we're just looking for a slope. And you guys know how to find slope. In this case, we're calling it a secant because it's a rate of change. And we're dealing with a line through a curve to get an average slope. This isn't perfect because it's not straight lines that we're getting the slope of anymore. It's curves. And if you notice, over here, right, it's not perfect where we're finding that secant, right? We're leaving some stuff out. We're not getting an exact point on that slope secant slope, or I don't know how they want to call it, secant slope, I would think. So, oh, that's the same exact slide. So cool. So we can come here and we can look at this, right? And this is where I lost you guys earlier, so I want to make sure and do well with it, even though it's solved on the other side already. I want to take you from one to the next fairly easily. So we're saying that this right here is the function we're using, right? And they're saying, well, what is the difference of that function when x equals -2 or when x equals 1? So the first thing we have to find out is what is our y for this, right? So I know right now when I have the point -2, I need to know what my y value is going to be, or what my f of x of 1 is going to be, right? And so I'm going to start by plugging in to this first one. We'll call it f of x of 1. This is terrible pen for writing with. Let's switch here. Right, our f of x of 1 is basically saying what is this equation when I plug in -2 for x. So what is f of -2 for this x cubed minus 3x? And so it just means wherever I see an x, I'm going to plug in -2. Now I'm going to put them in parentheses, whatever I plug in, my x values, because I want to know that I'm cubing that negative as well. Right? So here I'm going to have -2 times -2 times -2, which is -8. -3, -3 times -2 is +6, which is going to give me a solution of -2. So I know that this point is going to be -2, -2, right? Now, that's just my x1, y1. Remember, we're doing A here. So I have to do the same thing for the x2 value. So my x2 value is -1. We need to figure out what the y value is going to be, the f of x2. And we're going to do the same thing. We're going to take f of -1, because that's what we're inputting, right? And I'm going to write that as, okay, it's -1 cubed minus 3 times -1. And now we're going to solve it. And we're going to go, okay, here we've got -1 cubed. Well, that's just -1. -3 times -1, that's +3, which is going to give me +2. So these are my 2 points. This is not my solution. Now I have to use these to find the slope. And we're calling it slope secant, but M is still just slope. They just do a little SEC there so you know it's the slope of the secant line. But it's going to solve the same way as we would solve a slope from algebra 1 even, right? When we first started doing it and you did it in geometry. So we're going to take we can do y1 or y2, doesn't matter. But let's do y2 minus y1. So if I do that, I've got 2 minus 2, right? Because it's already 2 minus, but I'm subtracting it from a negative. And then we have negative 1 minus 2, right? And what's going to happen there is we are going to go, this becomes a plus, right? 2 minus 2 is the same as saying 2 plus 2, which is 4. 1 minus 2 is like saying negative 1 plus 2, which is just 1. So we're going to have a slope of 4. M secant is going to be 4. And hopefully on this next slide, they show the same thing I just did, only neater. I don't know. I can't get this stupid thing to move right now. Probably because I made it too big. Slide it over this way. So if you look at this, they didn't plug it into the equations like I did. I just showed you how it plugged in. They took f of negative 1 minus f of negative 2. And all they did was plug these in, right? This is f of negative 2 is negative 2. F of negative 1 is positive 2. And so they wound up with the same answer, right? But they didn't show you all the steps they took to get there. So if we look at it in terms of B, our B answer is, we got to go back to our B equation, and B is asking for 0 and 1, or x1, right? So same equation, but this time we're saying we want x of 1 equals 0 and x2 equals 1. But our f of x is still the same equation, right? Our f of x is still x cubed minus 3x. So we're going to have to go in and figure all that out, right? So I know x1 is 0, but I don't know what y1 is yet, right? I know that x2 is 1, but I don't know what y2 is yet, right? So this is x2, this is y2. So I just have to plug these numbers in and figure it out. So for x1, I would go, okay, well, this is 0 cubed minus 3 times 0. Well, that's going to make my life really easy, right? Because everything just becomes 0, right? For my x2, I'm going to plug in 1. So I would have 1 cubed minus 3 times 1. And I would figure that one out, right? And it would just be 1 minus 3 equals negative 2. So I have my numbers, right? But I just wanted to show you, because they don't show you how they got the 1 and 0, right? How they got the negative 2 minus 0. But you have to plug it in and find it. And then you're just going to look for the slope of the secant. So you're going to go m secant equals, and we're going to take our y2, which is negative 2, minus our y1, which is 0. And we're going to do it our x2, which is 1, minus our x1, which is 0. And we're going to have negative 2 over 1, which just equals negative 2, right? That is how they got there. So it's just plugging numbers into the equation and solving. I don't know how far along we are in this video yet, but I want to talk to you a little bit about even and odd functions before I move on. Now, you guys have done symmetry before. In terminology of functions, a function is said to be even when its graph is symmetric with respect to the y-axis. That means if I folded the graph in half at y, it would be the same on both sides, right? And and that would be an even function. An odd function is when it's symmetric to the origin. Now, the origin means where x and y meet, right? Which means that it would be like if you folded it in half vertically through them, it would work. The best way to do it is for each x in the domain of f of negative x equals f of x. So f of negative x would be your y. But we're going to look at it a little bit better, have it explained a little bit better right here. So when we're talking even and odd functions, so here we've got the same, basically similar to the equation we were just working with. It says that the function g of x equals x cubed minus x is odd because g of negative x equals negative g of x. And the way that we follow that is go, okay, if I input negative x into this equation and what I came out with was negative g of x, we would have an odd function, right? Because all we're changing is we're flipping the x value, right? So if I was on the positive side, everything's going to be the same, but now on the negative side of that y-axis, right? And that's how you're going to test for an odd function. So here they show it really well, right? When I plug in negative x, I get out a negative g of x. So if that was a number, say I was plugging in, say my negative x, say I had, if I plugged in 3 for this, I would get a solution. If I plugged in negative 3 for it, I would get negative of that solution. It's a test for an odd function. I'm hoping that we got an example here, but it doesn't look like it. For an even function, if I plug in negative x into the function, I get out a positive. So I want some examples here to be able to give you. And this is my last thing, my last slide, just showing you what it means to be symmetric about the origin. So this is an odd function, right? Everything on this side is repeating on this side. Everything on this side is repeating on this side. They're just opposites, right? They're flipped in both directions. We're flipping our x and our y values. So my positive x's become negative x's. My positive y's become positive y's. This one right here, you can look at it, right? If I fold this in half at y, if I fold a parabola in half at y, these are the same on both sides. They would line up entirely, right? So I would really like to show you a problem with that, but I did not create one for you. So I will post one separately online in just a picture and explaining it, because I want this video to end for you guys because it's getting kind of long, and I want to go to lunch. So if you have any questions, feel free to email me. I will do a couple sample problems of even and odd functions separately, and you can watch them if you choose to. But other than that, we will end this for now, and I'll just post it to PowerSchool for anyone who needs it.